Welcome to the deep dive. Today, we're really getting into the weeds of high-level network engineering. We've got a set of expert-level interview questions, the kind you'd see for a CCIE certification, as our guide. Our mission today, to go beyond just the answers. We want to unpack the why behind these advanced concepts, find those aha moments, Think of it as getting a sharper view on how the internet's backbone really works and why certain design choices are so critical.
Exactly. And what's great about these questions is they're grounded in, well, real-world challenges. They force you to think deeply about designing, managing, and troubleshooting complex critical networks. We'll be exploring how data actually gets around efficiently, how networks stay secure, and how they're built to be resilient.
Okay, let's jump right in. Routing protocols are fundamental. You always hear OSPF and EIGRP mentioned. Beyond the basics, what are the really key differences an expert needs to consider when choosing between them?
That's a perfect starting point. So OSPF, it's open standard linked state, uses Dijkstra's algorithm. Its real strength is in scalability, using those areas to build a very detailed topological map. Great for large, maybe multi-vendor networks. EIGRP, originally Cisco, but open now, is, well, often called an advanced distance vector or hybrid protocol. It uses the DUAL algorithm.
DUA, right? That's the diffusing update algorithm.
Yes, exactly. And its big advantage is incredibly fast convergence. It actively looks for loop-free backup paths before the main path even fails.
Ah, so it's proactive in finding a backup.
Precisely. It finds what's called a feasible successor.
Hmm.
If the primary route goes down and there's a feasible successor in the topology table, EIGRP can switch almost instantly. Sub-second failover is possible.
Okay, so OSPF gives you that detailed map, great for complex topologies, while EIGRP is all about speed and simpler setup, especially if you're mostly Cisco.
That's a good way to put it. EIGRP's convergence speed is often a major selling point for environments needing really high availability for real-time applications.
Makes sense. Now, things get tricky when you mix protocols, right?
All right.
Like redistributing routes between OSPF and EIGRP. What are the big pitfalls there, especially around preventing loops?
Oh, absolutely. Redistribution is notorious if you're not careful. The first most critical thing is setting metrics manually. OSPS cost and EIGRP's composite metric are totally different beasts. You can't just dump one into the other. You need that redistribute OSPF one metric dot command in EIGRP, specifying bandwidth, delay, reliability, load, MTU. Get those wrong, and you'll get suboptimal routing or worse, traffic just disappearing.
Black holes, yeah. Not good.
Definitely not good. And then there's the loop prevention aspect. You need to stop routes learned via EIGRP from being fed back into OSPF, only to be redistributed back into EIGRP again somewhere else.
Creates a nasty loop. How do you stop that?
Typically using route tags and route maps. You can tag routes as they enter EIGRP from OSPF, for example, with route map BLCK tag 10. Then on another redistribution point, you filter based on that tag, essentially saying don't redistribute anything with this tag. It breaks the potential circle.
Got it. Filtering with tags. Okay, let's shift to the heavyweight, BGP. It's all about the attributes for path selection. Which attributes are most often manipulated for, say, traffic engineering?
BGP attributes are definitely the control knobs. You have the well-known mandatory ones like AcePath, NextHop, Origin, they have to be there. But for influencing traffic flow, LocalPref and MED are usually the go-to tools. LocalPref is well-known discretionary. It tells your own routers within your AS which exit path to prefer if you have multiple connections to the outside world. Higher LocalPref wins.
So LocalPref controls how your traffic gets out.
Exactly. You use it to say, send traffic destined for X out via ISP-A instead of ISP-B. Maybe because A has more bandwidth or lower latency. MD, the multi-exit discriminator, is optional non-transitive. It's used to influence how other autonomous systems send traffic to you. Lower MD is preferred.
Ah, so MED controls how traffic comes in.
Precisely. You advertise a lower MED value on the link you prefer your neighbor to use when sending traffic towards your network. It's about influencing their decision.
Okay, local pre for outbound, MED for inbound. That clears it up. Now, the BGP best path selection process itself, it's famously complex. Can you walk us through that order? It's not just one factor, is it?
Not at all. It's a strict sequential process. BGP routers go down a list. First, they check the weight. That's a Cisco-specific attribute, locally significant only. Highest weight wins.
Okay. Wait first, then.
Then, highest local preference. We just talked about that one. After local pre-ref, it looks for the path originated locally by the router itself.
Makes sense. Prefer your own routes.
Right. Next is shortest ACE path. Fewer AS hops is generally better. Then it checks the origin code.
Yeah.
IGP is preferred over EGP, which is preferred over incomplete.
IGP, EGP, incomplete. Got it.
After origin, it's lowest MED. Remember, lower is
Yeah.
better for MED. Then it prefers EBGP paths over IBGP paths. More trustworthy generally.
EBGP over IBGP. Okay.
Still going. If there's still a tie, it chooses the path with the lowest IGP metric to the BGP next hop router. Basically, how close is the exit point within your own network?
Almost there.
And finally, if all else fails, the tiebreaker is the lowest router ID of the advertising router. It's quite a list. Understanding that sequence is absolutely vital for predicting and troubleshooting BGP.
Wow. Yeah, that's intricate. Okay, let's move from the protocols deciding the path to how the actual hardware, the switches and routers, handle packets so fast. What exactly is TCM?
TCM, Ternary Content Addressable Memory. It's really clever hardware. Think of it as specialized, super-fast memory. Instead of looking up data by address, like normal RAM, you search by content.
Search by content. How does that work?
You give it a value, say a destination IP address or a source port, and it instantly tells you if that value exists and where, all in one clock cycle. The ternary part means it can match on 0, 1, or don't care, which is perfect for things like network masks or wildcard rules in ACLs.
So it's incredibly fast for matching complex rules like ACLs, QX.
Exactly. It allows switches and routers to perform complex layer 2 to layer 4 lookups, checking source and destination IPs, ports, protocols, all simultaneously and at hardware speed. That's how you get line rate forwarding, even with complex policies applied.
Okay, so TCM is the hardware muscle. How does that relate to the ARB-EMEA FIB that we hear about?
Good question. They work together. The RBE, or Routing Information Base, is essentially the router's main database of all known routes. It's built by the routing protocols, the control plane. It holds all the potential paths. But the IB isn't optimized for speed. For actual packet forwarding, the router compiles the best routes from the RUB into the FIB, the forwarding information base. The FIB is structured for extremely fast lookups.
So the FIB is like the RIB's greatest hits, optimized for speed.
Pretty much.
Yeah.
And the FIB is often loaded into TCM or memory very close to it, so that when a packet arrives, the forwarding decision, based on the destination IP, can be made instantly by the hardware. This whole process is what Cisco calls CEF, Cisco Express Forwarding. RIB is control plane, FIB CES is data plane.
Right. Control plane makes the decisions, data plane executes them quickly using the FIB and TCM. What if you want to override that standard FIB lookup based on policy, not just destination? That's policy-based routing, PBR, right?
Exactly. PBR lets you sidestep the normal destination-based routing. You can say, if traffic comes from this source IP, or if it's this type of application, then don't just use the FIB, send it out this specific interface or via this specific next hop router, even if the FIB says otherwise.
How do you set that up?
Usually with route maps. Route maps are super flexible. You use them to match traffic based on criteria. Maybe an access list identifies the traffic, or a prefix list matches certain networks. Then the route map applies an action, like set IP next hop or set interface.
And why would you do that?
Lots of reasons. Maybe force web traffic through a specific security appliance, or send voice traffic over a dedicated low latency link, or ensure traffic from a critical server always uses a backup path for compliance. It's about applying business logic on top of the network's routing logic.
Very powerful. Okay, shifting to some broader network services, MPLS multi-protocol label switching. It's everywhere in service provider networks. What's the real magic behind it compared to just plain IP routing?
The magic is in the labels. Instead of routers doing a full IP header lookup at every hop, which involves checking the routing table, MPLS attaches a short fixed link label to the packet when it enters the MPLS cloud. Routers inside the cloud, the label switch routers or LSRs, just look at the label. We use the label to index into a table the LFIB, Label Forwarding Information Base, which tells them instantly what operation to perform, like swapping the label for a new one and sending it out a specific interface.
So it's much faster because it's a simple label lookup and swap, not a complex IP route lookup.
Exactly. It's more like switching than routing inside the core. This speed and efficiency is one reason it scales so well, but the other huge benefit is how it enables services.
Like VPNs and traffic engineering.
Precisely. MPLS VPNs use labels to keep different customers' traffic completely separate, even on the same shared infrastructure. Each VPN gets unique labels. For traffic engineering, MPLS allows you to create explicit paths, called label-switched paths, or LSPs, that don't have to follow the normal IGP shortest path.
So you can force traffic down a specific route, maybe one that's less congested or has better QoS guarantees?
Yes, you can engineer paths based on constraints like bandwidth or latency, giving you much finer control over how traffic uses the network compared to just relying on IGP metrics.
And closely related to MPLS VPNs is the concept of VRFs, right? Virtual routing and forwarding. What's that about?
VRFs are essentially virtual routers living inside a single physical router. Each VRF instance has its own independent routing table, EVAB, and set of interfaces. It's layer 3 segmentation, much like VLANs provide layer 2 segmentation.
So it isolates routing domains.
Completely. On a service provider edge router running MPLS VPNs, each customer connection would typically terminate into its own VRF. This ensures customer A's routes never mix with customer B's routes, even if they accidentally use the same private IP addresses. It's fundamental for multi-tenant security and isolation.
Makes sense. Okay, let's talk resilience. Layer 2 loops are terrifying. Spanning tree protocol is the classic answer, but it has evolved, hasn't it?
Oh yes, the original FTP, 802.1d, is quite slow. Convergence takes 30 to 50 seconds after a topology change. That's just too long for most modern networks.
Yeah, half a minute of downtime isn't great.
Not at all. So we move to RSTP, Rabbit Spanning Tree 802.1w. It optimizes the process, gets convergence down to like under 6 seconds in many cases, sometimes much faster. It's backward compatible too.
That's much better. What about networks with tons of VLANs? Running RSTP for every single VLAN seems inefficient.
It is. That's where MST comes in. Multiple Spanning Tree 802.1s. MST lets you group multiple VLANs into a single spanning tree instance. So instead of calculating paths for hundreds of VLANs independently, you might only run a few SDP instances. Much more scalable and less CPU intensive for the switches.
Okay, so RSTP for speed, MST for scalability with VLANs. And for making sure the default gateway is always available, we use things like HSRP.
Right. First hop redundancy protocols are FHRPs. HSRP, Hot Standby Router Protocol, is the Cisco's popular one. You configure 2 or more routers to share a virtual IP and virtual ASCII address.
A virtual gateway address?
Exactly. The end devices use this virtual IP as their default gateway. One router is active and handles the traffic for that virtual IP. Another is standby. If the active router fails, the standby router detects the failure and takes over the virtual IP and MACs almost immediately.
So the transition is seamless for the end users?
Largely seamless, yes. There's a very brief interruption, but way faster than waiting for routing protocols to reconverge. It provides crucial gateway redundancy.
Excellent. Let's touch on security. NAT network address translation. What's the key difference between stateful and stateless NAT?
The key is session tracking. Stateless NAT is a simple, fixed one-to-one mapping. An internal IP is mapped to an external IP, and that's it. It doesn't keep track of active connections. Stateful NAT, on the other hand, dynamically builds a table of active sessions. When an internal host initiates a connection to the outside, the NAT device records the source of destination IPs and ports. It then allows return traffic that matches an entry in its state table.
And stateful NAT often uses PAT, port address translation.
Very often, yes. PAT is a form of stateful NAT, where multiple internal private IPs are mapped to a single public IP, but using different source port numbers to distinguish the sessions. That's how most home and small business routers work multiple devices sharing one public IP. Stateful tracking is crucial for that to work securely.
Okay. For secure connections over public networks like the internet, we use VPNs. DMVPN is a common one. What's special about dynamic multipoint VPN?
DMVPN is really elegant for building scalable site-to-site VPNs, especially in hub and spoke or even dynamic mesh topologies. It uses a combination of MGRE tunnels, multi-point generic routing encapsulation, and NHRP, the next hop resolution protocol.
MGRE and NHRP, how do they work together?
The MGRE tunnel interface on the hub allows multiple spoke sites to connect using a single tunnel configuration. NHRP is like an ARP for the VPN overlay. Spokes register their public IP addresses with the hub. When one spoke wants to talk directly to another spoke, it queries the NHRP server, usually the hub, to get the other spoke's public IP. Then it can build a dynamic direct tunnel to that spoke, bypassing the hub for data traffic. It's dynamic and scalable, avoiding the need to configure tunnels between every single pair of sites.
So it enables direct spoke-to-spoke communication dynamically. That's clever.
Very clever, yes. Reduces load on the hub and latency for spoke-to-spoke traffic.
And the security for DMVPN and many other VPNs often relies on IPsec, right? How does IPsec actually establish a secure tunnel? What are the phases?
IPsec is the workhorse for VPN security. It works in 2 main phases. Phase 1 is about setting up a secure channel for the control plane communication. This uses IKE Internet Key Exchange, sometimes called ICMP. The goal here is to authenticate the peers and negotiate a security association, SA, for IKE itself. They agree on encryption, hashing, authentication methods, and generate shared keys using Diffie-Hellman.
Okay, phase 1 sets up the secure control channel, then phase 2.
Phase 2 happens inside the secure channel established by Phase 1. Here, the peers negotiate the actual IPsec SAs that will be used to protect the user data. They agree on the specific security protocols, usually ESP, encapsulating security payload, for encryption integrity, or sometimes AH, authentication header, for just integrity and authentication. They also define what traffic should be protected by this SA, often using access lists.
So phase 1 secures the negotiation. Phase 2 secures the actual data traffic using ESP or AH.
That's the essence of it. It provides confidentiality, integrity, and authentication for the data flowing through the VPN tunnel.
Got it. Stepping back a bit, we often hear about different planes and networking devices, control, data management. What's the distinction?
That's a really important architectural concept.
Yeah.
It helps to understand how a device logically separates its functions. The control plane is where the thinking happens. It runs the routing protocols, OSPF, BGP, etc., builds the routing table, RAB, calculates paths, runs spanning tree, things like that. It dictates how traffic should flow.
Okay, control plane is the brain, data plane.
The data plane or forwarding plane is the workhorse. It's responsible for actually moving packets based on the decisions made by the control plane. This is where the FIB and CEF operate, doing the fast lookups and forwarding packets from input to output interfaces, often in hardware like ASICs or TCM, high speed, low latency.
And the management plane.
The management plane is how we interact with the device. It's used for configuration, monitoring, and management tasks, things like SSH, Telnet, hopefully not, SNMP, Netcon, RESTCon. It provides access to configure and observe the control and data planes. Keeping these planes distinct is important for performance and security.
Makes sense. Control thinks, data does, management oversees. Finally, how do networks prioritize important traffic, like voice or video, over less critical data? That's QoS, right?
Yes, quality of service or QoS. It's a whole suite of tools, really, designed to manage network resources like bandwidth and buffer space to ensure different types of traffic get the treatment they need, especially during congestion.
What are the main components?
It usually starts with classification and marking. You identify different types of traffic, HE, voice, video, bulk data, using ACLs or NBAR, network-based application recognition, and then you mark the packets, often using DSCP, Differentiated Services Code Point, in the IP header, or HEBus class of service in the Layer 2 header.
So you label the traffic first, then what?
Then you apply policies based on those markings. This involves queuing strategies, how packets wait in line when there's congestion. Instead of simple FIFO, first in, first out, you might use CBWFQ, class-based weighted for queuing, to guarantee bandwidth percentages to different classes, or LLQ, low latency queuing, to give strict priority to real-time traffic like voice.
So priority lines for important stuff.
Exactly. There's also congestion avoidance, like WRED, weighted random early detection, which starts dropping less important packets before queues become totally full, preventing complete gridlock. And finally, policing and shaping, which enforce traffic rates. Policing drops excess traffic, shaping delays it, buffers it, to smooth out bursts. It's a whole toolkit.
Wow. Okay, that covers a lot of ground. What really stands out here is that none of this is just academic. These are the tools and concepts used every day to build, manage, and troubleshoot the networks we all rely on.
Absolutely. Understanding these concepts deeply, the why and how, not just the what is what separates basic administration from true network engineering. It's about designing for performance, resilience, and security from the ground up.
And our source material pointed out other real-world complexities too. Things like handling BGP route flapping, dealing with asymmetric routing problems, configuring multicast, designing robust VPN failover, and increasingly understanding SDN fundamentals.
Right. The theory constantly meets messy reality. Knowing these core principles gives you the foundation to tackle those complex, evolving challenges.
So connecting this all together, mastering this level of detail, really means you're equipped not just to follow procedures, but to actually architect and troubleshoot these incredibly complex systems that keep our digital world running.
I couldn't have said it better. It's about understanding the engineering principles behind the protocols and hardware.
Which brings us to a final thought for you, our listener. As networks get even more complex, with things like cloud integration and software-defined networking becoming mainstream,
It raises an important question. How do these fundamental principles, routing logic, hardware forwarding, security mechanisms, redundancy, how do they continue to apply or maybe even evolve in these new paradigms? Which of these concepts might become even more critical as we move forward?
Something to chew on. What a deep dive. Thanks for joining us on this exploration into the heart of network expertise.